When we classify dams, we categorize them by their use, their hydraulic design, and most crucially, their construction material. That material divide separates the engineering world into two distinct philosophies: rigid structures, like concrete, and non-rigid structures, like compacted earth. A concrete gravity dam is a massive, immovable object. It fights hydrostatic pressure entirely through dead weight and basic statics. We can see this reliance on material density directly in the mathematics. Looking at the solution for minimum base width, the equation B equals h over square root g minus c shows exactly how the material's specific gravity, the g variable, dictates the required footprint to resist overturning and sliding. Earth dams operate on different physical principles. Instead of a solid, impervious monolith, they are assembled from millions of disconnected soil particles. They are permeable, flexible, and yield under stress. This creates a distinct engineering paradox. The structure exists to retain water, but because the soil is particulate, water is the greatest threat to its own structural integrity. You cannot simply pile dirt across a river valley. An earth dam is a multi-layered filter system engineered specifically to manipulate the flow and internal pressure of water. Every element of its complex cross-sectional geometry exists to defeat three distinct modes of failure: hydraulic, seepage, and structural. We begin with the most statistically devastating vector. Hydraulic failures account for roughly 40% of all earthen dam collapses. The primary mechanism here is overtopping. When reservoir water exceeds the crest height, spilling over the top, the flowing water rapidly scours the downstream slope, cutting a deep V-shaped breach directly through the dirt. A solid concrete dam can often survive a minor overtopping event intact, but because soil lacks strong cohesive bonding, an earth dam undergoes immediate, catastrophic external erosion. Even without overtopping, the dam faces a hydraulic threat from the reservoir itself. Continuous wind-driven waves strike the upstream face, scouring away the soil over time. Defeating overtopping is a matter of strict capacity. Engineers must design massive, independent spillways and calculate rigorous freeboard limits to ensure the reservoir surface never reaches the dam's crest. To defeat the continuous wave scour, the upstream face is armored with heavy stone pitching, known as riprap, which dissipates the kinetic energy of the waves. Spillways and rock armor handle the external threats. The true challenge of earth dam engineering is managing water that inevitably penetrates the surface. That internal water leads directly to the second failure mode, seepage, which is responsible for nearly 30%. Below it, soil pores are completely filled with water. On this line, internal pore pressure equals atmospheric pressure. If a dam is built of a single uniform soil type, this phreatic line will naturally curve through the structure and exit out of the downstream face. This exiting water becomes lethal if its velocity exceeds the soil's critical hydraulic gradient. When water moves too fast, drag forces overcome the weight and friction of soil grains. Exiting water begins carrying those soil particles away with it. This hollows out a small tunnel. As the tunnel grows backward into the dam, the seepage path shortens, water velocity increases, and erosion accelerates until the entire structure collapses. To arrest this process, engineers introduce an impervious clay core in the center of the dam. The low permeability of the clay drastically chokes the total volume of water passing through. Reducing the volume is only half the battle. A slow leak exiting at the wrong location can trigger piping over time. The core alone does not safely manage the final exit path. This requires a downstream drainage system, typically consisting of a porous rock toe and a horizontal blanket drain placed at the base. These rock drains offer a path of zero resistance. When the seepage water hits the drain, the phreatic line is sharply pulled downward, keeping the saturation zone buried within the dam's foundation. The central clay core throttles the flow rate, while the rock drains guarantee the internal water never breaks through the downstream slope, eliminating the physical conditions required for piping. Even if the water is safely routed through the dam, the weight of the saturated soil can trigger the final failure mode, structural shear. When the gravitational stress on the soil exceeds its internal shear strength, sections of the dam can fracture and slide downward in rotational slip circle collapses. The downstream slope experiences its maximum structural stress during conditions of maximum steady seepage, when it is heavily loaded with internal water. The upstream slope faces a more complex threat, triggered by an operational scenario called sudden drawdown. If a reservoir is rapidly lowered, the external water level recedes faster than internal soil can drain. This creates a mechanical trap. The hydrostatic pressure supporting the soil vanishes, yet internal pore water remains trapped inside, pushing outward. In soil mechanics, this high internal pore pressure reduces effective stress. Without effective stress, soil friction drops, killing shear strength and triggering a massive landslide. Engineers counter this geometrically by designing the upstream slopes to be flatter than the downstream side, spreading the shear load over a wider base. They also use material mitigations. The core is enclosed in thick, pervious outer shells. These casings allow that trapped pore pressure to drain out quickly when the reservoir level drops. Structural stability is a delicate balancing act of manipulating effective stress by precisely controlling how fast internal water can escape. When we combine these solutions to overtopping, piping, and shear failure, the modern zoned earth dam profile emerges. This is a deliberate assembly of distinct materials, each performing a specific mechanical function. The central clay core exists solely to choke the total volume of internal seepage. The pervious shells prop in necessary mass while ensuring rapid drainage to maintain shear strength during sudden drawdown. And the downstream drains act as a trap for the phreatic line, guiding the remaining water safely out of the structure to prevent internal piping. This physical cross-section maps directly onto your required reference material. Looking at this table of contents, mastering sections 10.4 through 10.7 requires understanding exactly how these interactive zones prevent the failures listed in section 10.2. AEE candidates must analyze the earth dam as a pressure management system, where internal stability depends on the interplay between pore pressure and soil strength. But because an earthen structure cannot survive water flowing over its crest, mastering its internal stability is useless without mastering the external release valves. And that brings us to the geometry of spillway design.